Hi guys, today we're going to be doing Cambridge A-Level Further Mathematics 2020 May-June series paper 3-1. It's a further mechanics paper, so we'll be starting now. First question. A particle P is projected with speed u at an angle 30 above the horizontal from a point O on horizontal plane, and it moves freely under gravity. The particle reaches its greatest height at time t after projection. Find in terms of u the speed of p at time 2/3 of t after projection. So take note that we want to find the speed and not the velocity. So even if we have a negative number after this, we need to change it to a positive. So now we draw something like this. So we have initial speed u at an angle of 30 degrees, and at the highest point, this is time equals to t, and remember that at the highest point we have the vertical velocity as 0, alright, because it's changing the vertical direction at the highest point. So now we first need to find what is the capital T, the value of the capital T. So we can use V equals to U plus AT, this formula. So the vertical velocity would be 0 at the highest point, and U would be, the initial speed would be U sine 30. This is the vertical initial velocity, plus A would be negative 10, and time would be t. So we have 10t equals to 1 over 2u, and t would be 1 over 20u. So now we need to find for the velocity when p is at the time 2/3 of t. So the horizontal velocity would always stay the same because there's no horizontal acceleration. So horizontal velocity would be u cos 30, which is sec 3 over 2u, and the vertical velocity at time 2/3 t is u sine 30 plus negative 10 2/3 of t, which is 2/3 times 1 over 20u, right? So we have 1 over 2u minus 1 over 3u, and this would give us 1 over 6u. So for the speed, we need to take the square of horizontal velocity plus the square of vertical velocity and square root the whole thing. Alright, so we have 7 over 9u squared, square root the whole thing, which is equals to 7 over 3u. So this will be the final answer. Question 2. A light inextensible string of length A is threaded through a fixed smooth ring R. One end of the string is attached to a particle A of mass 3m, so A has mass 3m, and the other end of the string is attached to a particle B of mass m. so B as mass m. The particle A hangs in equilibrium at a distance x vertically below the ring. The angle between AR and BR is theta. The particle B moves in a horizontal circle with constant angular speed of 2 cert g over A. So this whole thing would be our omega. Show that cos is equal to 1/3 and find x in terms of A. So now we need to first figure out the forces in this diagram. So let's look at A first. In A, we have the weight of 3 mg. This is the weight. And we have tension T. And for B, because this is the same string, so the tension is the same, but in opposite direction, right? So this 2T has the same value. And B has weight mg. Okay, so for now, we know that at A, it is in equilibrium, right? That means the weight would be equal to tension right here. So we know that T would be equal to 3 mg. This is our first info. Okay, now at B, we would try to resolve this in the vertical and the horizontal direction. So now we can change T to 3 mg. Alright. And in the vertical component, we know that this angle right here is theta, right? This is alternative angle. So this would be theta. And in the vertical direction, this would be 3 mg cos theta. And in the horizontal direction, we have, sorry, it's not straight. Oops. In the horizontal direction, this would be 3 mg sine theta. So now we can remove this since we have resolved it in the vertical and horizontal direction. Okay. So at B, the vertical forces should be equal to each other, right? Because the only net force is towards the center of circle, which is our centripetal force. So this would be the only net force that is in B. So these two must be equal. So we know that 3 mg cos theta is equal to mg. So cancel mg out. We have cos equal to 1 over 3. And this is what the question wants. So now let's find out what sine theta is. So let's say this is our theta. Cos theta equals to 1 over 3. So 1 over 3. So what is this value here? We have 3 square minus 1 square square rooted, and we get 2 sub 2. So this value here is 2 sub 2. And sine theta is opposite over hypotenuse, which is 2 sub 2 over 3. Alright. So now we can look at the centripetal force. And we have the info about the constant angular speed of 2 sub g over A. So we know that centripetal force is equal to 3 mg sine theta, right? This is the net force that is available in B. And Fc, centripetal force, also has a formula of mr omega square, right? So now we have the omega and we need to find for the radius. So looking back at the diagram, this would be our radius, right? This would be r. But what is r? So we know that the string itself has length a. Okay? This whole thing is a. And this part is x. So the remaining here would be a minus x, right? So we can see that this is a triangle, right? This is a right angle triangle. So since we have the angle theta over here, we have a minus x over here. So what is r? R would be a minus x times sine theta, right? So now we know what is r, and we can plug in all the info into this formula. So we have 3 mg sine theta, which is 2 sec 2 over 3, equal to m times r, which is a minus x times sine theta, which is 2 sec 2 over 3, times omega square, which is 2 sec g over a square. So now we can cancel out m. We can cancel out 2 sec 2 over 3, and we have 3g equals to a minus x times 4g over a. And we can cancel out the g here as well. So we have 3a equals to 4a minus 4x. So 4x equals to a, and x equals to 1 over 4a. So this would be the answer. Question 3. One end of a light elastic spring of natural length a, so this would be our natural length, and modulus of elasticity 5 mg, is attached to a fixed point a. The other end of the spring is attached to a particle p of mass m. The spring hangs with p vertically below a, and p is released from rest in the position where the extension of the spring is 1 over 2a. Show that the initial acceleration of p is 3 over 2g upwards. So we have elastic string, and we have a particle over here. So the fixed point A is over here, and the particle P has mass m. So we have the weight mg, and we have tension force. So now we need to find for the initial acceleration. So we have F equals to ma, right? And we know that The F over here is the net force. So net force is equal to tension minus weight, right? And the formula of tension would be lambda x over L, right? So we have lambda, which is 5 mg, times x, which is 1 over 2a divided by a, the natural length, minus the weight, which is mg, equals to mass times acceleration. Since they already have a small letter a over here, right? I would use a big letter A to represent the acceleration, just to avoid confusion. So we can simplify this equation. We cancel out the m, cancel out the a, and now we have acceleration equals to 5 over 2g minus g. So we have 3 over 2g. So we prove that it's 3 over 2, but how do we prove that it's outwards? So what I will do is I will have a sentence to explain. So I will say the tension force upwards is greater than the weight downwards. So the initial acceleration is upwards. Done. Part B. Find the speed of P when the spring first returns to its natural length. Returns to its natural length means the extension is equal to 0, and that means there's no elastic potential energy at that position. So when we need to find for the speed, the equation that we can use is the conservation of energy, principle of conservation of energy. So we have the kinetic energy gain. Wait, let me first draw out the diagram. So it was like this initially, and now it becomes like this, maybe. So this is when the extension is 1 over 2a, and now it is at its natural length. That means it rises by 1 over 2a. So now we have the kinetic energy gain plus, plus the gravitational potential energy gain equal to the elastic potential energy loss. Okay, so we have the difference in the kinetic energy. Initially, it is released from rest, right? Released from rest. So the initial velocity is 0. So we just have to consider the final velocity, which is half mv square. V square is the one that we want to find, plus mgh. The height is 1 over 2a, equal to lambda, which is 5 mg, times extension square over 2 times the natural length. So we can cancel out the m, and now we have half v square plus 1 over 2 ag equals to 5 over 8 ag. So v square would be equal to 1 over 4 ag, and v is equal to plus minus 1 over 2 sub ag, right? And since they want the speed, we can just write speed is equal to 1 over 2 sub ag. Done. Question 4. A uniform square laminar ABCD has sides of length 10 cm. The point E is on BC with EC equals to 7.5 cm, and the point F is on DC with CF equal to X cm. The triangle EFC is removed, and the center of mass of the resulting shape ABEFD is a distance of x bar from CB and a distance y bar from CD. Okay, show that x bar is equals to 400 minus x squared over 80 minus 3x, and find the corresponding expression for y bar. So we can first draw out a table. So the first one would be the laminar, second would be area, third would be the distance of center of mass from CB. So the fourth one would be the distance of center of mass from CD. Yes. So after having these 4 columns, we can start filling in the information. So the first laminar would be ABCD, which is the original square laminar, and we need to minus the laminar of EFC, the one that is removed. So finally, the resulting shape is ABEFD, the one that we want to find for the x bar and y bar. So we know that the area of ABCD is 10 times 10, right? So we have 100 for the area of ABCD. And for EFC is basically half times base times height, right? So we have half times x times 7.5, which gives us 3.75x. And the resulting area would be 100 minus 3.75x. And for the distance of center of mass from CB, we know that for a uniform square, the center of mass would be right in the middle of the shape, right? So we have the distance of COM from CB is 5, and from CD is also 5. As for the triangle EFC, okay, now we can write out the coordinates of these 3 points. So starting from C, we view this as x and y coordinate, right? So this would be the x, and this would be our y. So starting from C, C would be 0, 0, right? F would be x, 0. E would be 0, 7.5. Now we need to find for the distance of COM from CB for EFC. So for the distance from CB is over here. So to find the distance from CB, we need to look at the x coordinates, right? So we just need to add this tree up, 0 plus 0 plus x, and we divide it by 3. So we have 1/3 of x. And for the distance of COM from CD is over here. So the distance would be here, right? So we need to look at the y coordinates. The y coordinates. So what we do is we add this 3 up, 7.5 plus 0 divided by 3. So we will get 2.5. And for the distance of COM from CB of ABEFD, we know that this is x bar and this is y bar. And these two are the unknowns that we need to find for. So for x bar, we can take the product of these two minus the product of these two equals to the product of these two, right? So basically x bar is equals to product of these two minus product of these two divided by the area of ABEFD. So we have 100 times 5 minus 3.75x times 1/3 x over 100 minus 3.75x. So we can simplify it to 500 minus 5 over 4 x squared divided by 100 minus 15 over 4 x. And to further simplify it, we can divide this by 5 over 4, 5 over 4, and now we have 400 minus x squared over 80 minus 3x. This would be our our x bar, right? Exactly the same. So for our y bar, let me draw a line over here. So for our y bar, we do the same thing, but for this column. So we have this 2, the product of this 2, minus the product of this 2, divided by this. So 100 times 5 minus 3.75x times 2.5 divided by 100 minus 3.75x. So we have 500 minus 75 over 8x over 100 minus 15 over 4x. So now we can simplify it to, we can times 8 for both the numerator and denominator. So we have 4000 minus 75x over 800 minus 30x. And to further simplify it, we can divide 5 for both denominator and numerator. So we have 800 minus 15x divided by 160 minus 6x. So this would be our y bar. Part B. The shape ABEFD is in equilibrium in a vertical plane with the edge DF resting on a smooth horizontal surface. Find the greatest possible value of x, giving your answer in the form a plus b sub 2, where a and b are constants to be determined. So it's resting on the edge of DF, which is, um, let me use green, so we have this surface here. It's resting like this. So now we need to find for the greatest possible value of x. And let's say this is our center of mass. We know that our center of mass has to be in this range, right? It cannot be over here, because if it's here, the weight goes down like this, the whole lamina will topple in this direction, right? So our center of mass must be at least along this line, maybe over here. This is the most left it can go. So now we know that now we know that this is x bar and this is x. So x bar can be from x all the way to this point, right? Our center of mass can go from here all the way to this point. So we know that x bar is for sure larger than x. Can you see that? The distance of the center of mass from CB must be larger than x. So when, let's say x bar, let's say the COM is over here, then x bar would be this distance. So now we use the fact that x bar is larger than x, and now we can sub x bar in, which is 400 minus x squared divided by 80 minus 3x larger than x. So we have 400 minus x squared is larger than 80x minus 3x squared. So 2x squared minus 80x plus 400 is larger than 0. And x squared minus 40x plus 200 is larger than 0. So now we find for the x value. X is equals to negative b plus minus b squared minus 4ac square root divided by 2a. So this would give us 40 plus minus 20 sub 2 over 2. And we would get 20 plus minus 10 sub 2. So the inequality that we will get is x less than 20 minus 10 sub 2, or x more than 20 plus 10 sub 2, right? And we know that the lamina itself, the distance over here, is already 10. So the center of mass can't be over here, right? If it's more than 20 plus 10 sub 2, it would be around like this part, which doesn't make sense at all. So this inequality is rejected, and we will only take this one. So we know that the greatest possible value of x is equal to 20 minus 10 set 2. Question 5. A particle P is moving along a straight line with acceleration 3 ku minus kv, where v is its velocity at time t. U is its initial velocity, and k is a constant. The velocity and acceleration of P are both in the direction of increasing displacement from the initial position. So increasing displacement means positive direction. So velocity and acceleration are both positive. Find the time taken for P to achieve a velocity of 2u. So for now, we only have the info that acceleration is equals to 3ku minus kv. So we would use that. So acceleration is dv over dt. So we know that dv over dt equals to 3ku minus kv. And we will need to separate them. So we have the integration of 1 over 3ku minus kv dv is equal to integration of 1 dt. So for this part, all this are just constants. So we have negative 1 over k ln 3ku minus kv is equal to t plus c, which is a constant. So another info is that when t equals to 0, v is equal to u, because u is the initial velocity. So we have at t equals to 0, v equals to u. So negative 1 over k ln 3ku minus ku equals to 0 plus c. So c would be equal to negative 1 over k ln 2ku. So we need to find for the time taken to achieve a velocity of 2u. So basically, sub v equals to 2u. So we have negative 1 over k ln 3ku minus 2ku equal to t minus 1 over k ln 2ku. So t is equal to 1 over k ln 2ku minus 1 over k ln ku. So now we have 1 over k ln 2ku over ku. Alright, so this would be equal to 1 over k ln 2. Done. Part B. Find an expression for the displacement of P from its initial position when its velocity is 2u. So if we want to find for displacement and we have the information about the velocity. So we can use the formula of A equals to V times dV over dx. So we have V dV over dx equal to 3Ku minus Kv. So now we separate them into V and x. So we have V over 3U minus V dV equals to integration of K dx. So this is so we can write this as negative 3U minus V plus 3U for the numerator, and denominator remains the same. And for the right side, we can integrate it first. So we have kx plus c. And now we can separate this into two fractions. This is one fraction. This is the second fraction. So we have negative 1 plus 3u over 3u minus v. And now we can start integrating. So we have negative v minus 3u ln 3u minus v equals to kx plus c. So now we need to find for the constant c. We know that the initial velocity is u when the particle is at the initial position. So when x equals to 0, v equals to u. So we have negative u minus 3u ln 3u minus u equal to c. So c would be equal to negative u minus 3u ln 2u. Okay, so when v equals to 2u, which is what the question wants, we need to find for the displacement. So negative 2u minus 3u ln 3u minus 2u equals to kx minus u minus 3u ln 2u. So kx equals to 3u ln 2u minus 3u ln u minus u, which is also equal to 3u ln 2, because 2u divided by u is 2, minus u. So x will be equal to u over k times 3 ln 2 minus 1. That. Question 6. A particle P of mass m is moving with speed u on a fixed smooth horizontal surface. The particle strikes a fixed vertical barrier. At the instant of impact, the direction of motion of P makes an angle alpha with the barrier. The coefficient of restitution between P and the barrier is E. As a result of the impact, the direction of motion is turned through 90 degrees. Show that tangent square alpha equals to 1 over E. So we have a vertical barrier and our particle strikes the barrier and turns through 90 degrees, like this. So this is the initial speed, and this is the final speed. We know that this angle is alpha, and this is 90 degrees. That means this angle would be 90 minus alpha. Okay, so we can start doing it now. For the vertical motion, vertical means in this direction. We know that the speed doesn't change, right? So we have we know that the momentum, the vertical momentum, the momentum in this direction doesn't change. So we have mu cos alpha equals to mv cos 90 minus alpha. So we have u cos alpha equals to v sine alpha. And for the horizontal momentum, that means we resolve the velocity in this direction. We know that we need to use the information that the coefficient of restitution is E. So we need to use the formula of V1 minus V2 equals to negative E times U1 minus U2. So since we actually hit the barrier doesn't move, so this and this would be treated as 0. So we just need to consider these two. So now V1 would be, we fix that to the left would be negative and to the right would be positive. It will be easier. So V1 is negative V sine 90 minus alpha equal to negative E times U sine alpha. So we have U sine alpha V cos alpha equals to EU sine alpha. So this is the first equation, this is the second equation. So now we take the first equation divided by the second equation. We can actually change the first equation to V sine alpha equals to U cos alpha. This would make it look easier. So first we have V sine alpha divided by V cos alpha, which is tangent alpha. And for the right side, we have U cos alpha divided by EU sine alpha, which is 1 over E tangent alpha. So now tangent square alpha equals to 1 over e. Part B. The particle loses 2/3 of its kinetic energy in the impact. Find the value of alpha and the value of e. So that means the final kinetic energy is only equal to 1/3 of the initial kinetic energy. So we have the final kinetic energy, half mv squared, equals to 1/3 of the initial kinetic energy, half mu squared. So cancel this two out. We know that v squared equals to 1/3 of u squared. And that means u squared over v squared is equal to 3. We call this the third equation. And from the first equation, we know that v sine alpha equals to u cos alpha. V sine alpha equals to u cos alpha. So u over v will be equal to tangent alpha. We call this the fourth equation. So we sub 4 into 3, and we can see that tangent square alpha equals to 3. So tangent alpha is plus minus 3. So alpha would be 60 because it has to be an acute angle. So we already found the value of alpha, and now we need to find for the value of e. And from the first part, we know that tangent square alpha equals to 1 over e. So tangent square is 3. So we have 1 over e equals to 3 and e equals to 1 over 3. Done. Question 7. A hollow cylinder of radius a is fixed with its axis horizontal. A particle p of mass m moves in a part of a vertical circle of radius a and center O on the smooth inner surface of the cylinder. The speed of p when it's at the lowest point a of its motion is 7 over 2 ga. The particle p loses contact with the surface of the cylinder when OP makes an angle theta with the upward vertical through O. So basically we have a circle. This is the vertical. O is right here. And now we have two situations. When the particle p is at the lowest point, the speed is 7 over 2 ga. When the particle is theta, when the particle makes an angle of theta with the upward vertical, which is this part, it loses contact. Loses contact means our contact force equals to 0. Alright? So now we have to show that theta equals to 60. Okay. So let's look at this situation first. So here we have the force of the weight, which is mg, and nothing else. We don't have contact force, we don't have anything. So now we need to resolve the weight in the direction towards the center of circle and 90 degree to the center of circle. So we know that this is also theta because it's a alternative angle. So towards the center of circle, we have mg cos theta. And 90 degrees to the center, which is tangent to the circle, we have mg sine theta. So now we can remove this. Okay. So we know that the centripetal force is equal to the net force, and it's also equal to mv squared over r. R being the radius of the circle. So radius, we know that it's a. And we can start doing it. So the net force is mg cos theta equal to mv squared over a. So we cancel m, and we know that v squared equals to ag cos theta. So we know the speed of the particle when it loses contact with the surface of the cylinder. And now we can consider the principle of conservation of energy. So when it moves from this part all the way to this part, it gains gravitational potential energy, right? So we have GPE gain equals to the KE loss. So how do we know the height? So we know that this is also A because this is also the radius. What about this height over here? What about this part? So we know that this is A, this is theta, and this is a right angle triangle. So we know that this is A cos theta. So the height will be A cos theta plus A. So the GPE gain would be mg times A plus A cos theta. And the change in the kinetic energy would be half m times the final velocities, the initial velocity square minus the final velocity square. So the initial velocity or the initial speed is cert 7 over 2 GA. So we have cert 7 over 2 GA square minus the final velocity square, which we already found just now, ag cos theta. So now we can simplify the equation. We can cancel mg. Maybe cancel a as well. So now we have 1 plus cos theta equal to half times 7 over 2 minus cos theta. So now I have 1 plus cos theta equal to 7 over 4 minus 1 over 2 cos theta. That means 3 over 2 cos theta is equal to 3 over 4. And cos theta would be 1 over 2. So theta would be 60. Done. Part B. Show that in its subsequent motion, P strikes the cylinder at the point A. So let's draw the circle again. This is the vertical. This would be O. This would be A. It loses contact over here when theta is 30 and 60. I'm so sorry. So alright, so it says that we need to prove that P strikes the cylinder at point A. That means after losing contact, the particle goes like this, strikes A. And the direction of the velocity is always tangent to the circle. So we have the direction of velocity like this, in this direction, and V would be equal to sub AG cos theta. So let's sub it in first. V squared equals to AG cos 60. So V would be 1 over 2 AG squared. So we know that V is square root 1 over 2 AG. So now we can start doing the actual question. How do we prove that it strikes A? So we need to prove that at the same timing, the horizontal displacement or the horizontal distance traveled is this distance over here, right? And the vertical distance traveled is this distance over here. Okay, so let's find for the time first. So we assume that, okay, never mind. We find for the time needed for the particle to travel a distance of this, which is so this is A, this would be A cos 60. Sorry, A sine 60. So when P is vertically below O, which means it's along this line, we need to find for the T. So we can use the formula of S equals to UT plus half AT squared. So S would be A sine 60 equal to U would be. So now we need to find for the horizontal velocity, and this angle here is also 60. So V cos 60 would be the horizontal velocity. So sec half AG cos 60 times T. And we don't have any horizontal acceleration, so we can just ignore this part over here. So we have T equal to sec 2A sine 60 over sec AG cos 60. And this would give us sec 6A over G. So we know that the time that we need to use would be sec 6A over G. So now we just need to find for the vertical distance traveled. At T equals to sec 6A over G, the vertical distance traveled is what we need to find. So we have Sy equal to, we use the same formula, yeah? So we have Sy equal to U, which is V sine 60, which is sec half AG sine 60 times sec 6A over G, that's the time, plus half acceleration is negative G, time square, which is sec 6A over G squared. So simplify it, we can cancel the G, and we have 3 over 2A minus 3A and we will get negative 3 over 2A. That means the vertical distance or the vertical displacement is negative 3 over 2A, which means it travels downwards. So conclusion, point A is 3 over 2A below the point where P loses contact. Therefore, P strikes A. That means this distance over here is exactly this distance. So we already proved that P strikes A.